Okay, so we're going to look at some group theory today, and in particular we're going to look at this square and what happens with the rotations and reflections along these lines of symmetry here. So we've got reflections here on the outside, reflection R, S, T, U. They're all denoted by the reflection along these lines. And in the middle you'll notice we've got some rotations. So these ones here, A is through pi over 2, B is a rotation through pi, and C is a rotation through 3 pi over 2. Now what we want to know is what happens to each of these points at the vertices of the square and where each point will end up at. So for example, if we rotate through 90 degrees, i.e. using the rotation A, where will 4 end up, and so on. So first of all, I'm going to draw up some two-line permutations. So let's concentrate first on this A. So A, we're going to work out what happens to each point when we rotate. So as we rotate through 90 degrees, so we're going to imagine turning the square this way, the 1 will end up at 2, 2 will end up at 3, 3 will end up at 4, 4 will end up at 1. So we can just write this in this form on this two-line permutation here. So 1 is the starting point, 2 is the end point, 2 is the start, 3 is the end, and so on. So that takes care of A. Now let's have a look at B. So B is a rotation through pi, so 180 degrees. So now a full half rotation of the square. So the 1 will end up at the 3, the 2 will end up in position 4, 3 will end up in position 1, 4 will end up in position 2. So permutation again we'll just write in the same manner. These are the starting points, then on the bottom we'll write the end points. So each one now is going to jump 2 places. Okay, so that takes care of B. Now C is a rotation through 3/4 of the rotation here, so that's 3 pi over 2. So all the way round, that there will 1 will end up at 4, 2 will end up at 1, 3 will end up at 2, and 4 will end up at 3. So let's write that down on the permutations here. Starting point again on the top, and then the end points. As you see, these will all be in numerical order. When you get to 4, go back down to 1. Okay, right. Now, we'll have a look now at the reflections. So we've got R, S, T and U. So R, let's write these in. So R is a reflection down the centre there. So if we reflect it, basically if we turn the paper over, what will happen to each of these points? So basically the 1 will end up at the 4 and the 4 will end up at the 1, and then the 3 and 2 will change places as well. So 1 ends up at 4, 4 ends up at 1, 2 ends up at 3, 3 ends up at 2. Now we take a similar rotation T. I'll just write a space here for S to go into, and then we'll write T here. Now T is very similar, where all the points will change place. So if we're going to rotate this way, 1 will end up at 2 and 2 at 1, and then 4 and 3 will change place in a similar manner. So we've got 1, 2, 3, 4. 1 ends up at 2, 2 ends up at 1, 3 in 4, and 4 in 3. Okay, so now we're going to look at S and U. Let's just write the U in here as well. Now these are slightly different to the T and the R rotations, reflection, sorry. The S one here, that's going to be flipped over this axis here. So the 1 and the 3 aren't going to change places on the S. So 1 will stay at 1 and 3 will stay at 3. But the 4 and the 2 will change places. So similar here with the U, this time the 2 and 4 will stay in the same place. So permutations will end up like this, but then the 1 and the 3 will change places. Okay, now there's one element here missing of these, is the identity element. So I'm just going to write that in here. E is the identity element. Because you'll see here we've got 7 different elements here. We need an even number for this particular shape here. So the identity is always the one, and all the identity tells us is we end up back where we started. So that one would just be a simply very trivial set, that one. Okay, so now what we're going to do is we're going to try and draw on some inverses. So the inverse of A, B, C, R, S, T, U and E, well the inverse of E is always E. Okay, so for the inverse of A, we're looking at what will happen with this rotation if we then go back again. So if point 1, where will we need to start at point 1? Where will we need to start at to end up at point 1? So here our inverse point will be point 4. So 1 will end up at 4. The 2 we'll need to start from point 1. The 3 will need to start from point 2, and the 4 from point 3. So you kind of see what is happening here. Now this inverse will always equal one of the other sets that we've drawn up. So we have a look down the line. Our inverse here, 4, 1, 2, 3 on the bottom line, is the same as C. Okay, so we can see here that the inverse of A is equal to C. So what we can say is that A composite with C gives us our identity. Now, as this is a cyclic group, we can also say that C acting on A is also our identity, because they will always end up back where they started from. Okay, now let's have a look at B, the inverse of B. So 1, 2, 3, 4. B is the rotation through 180 degrees. Now for 1, where will we have to start from? It would be 3. So starting from 3, so to get back to 2 we'd have to start from 4, and again using numerical order, 3, 4, 1, 2. Now we can see here that the inverse of B is the same as B. So basically this is what's called a self-inverse. So B composite with B is also the identity. Now C, this is a rotation through 270. So to get to 1, we would have had to start it from 2 to get back to where we wanted to be. So 1 would be 2, 2 would be 3, 3 would be 4, 4 would be 1. So you can check those, but you can see that you would always start from 1 previous. So the inverse of C is 2, 3, 4, 1, which is the same as A. So we could have worked that out from before, because A acting on C and C acting on A is also E. So that just proves that this group here is cyclic. So all the groups will always have inverses, which are A to C will give an inverse, and C to A will also give us an inverse. So this is a cyclic group. Okay, R. So what about the inverse of R? So R is a rotation, sorry, a reflection through this axis here. So for 1, we would have had to start it at 4. So 2 would be 3. 3 would have been 2. And 4 would have been 1. So which one is this equal to? So this one is equal to R. So here what we can say is that R is also self-inverse. Now, as these are reflections, we'll see that all of these are all self-inverse. So S to minus 1 equals S. So S, composite S, is the identity. And same for T. Let's just write these in. The inverse of T is also T. So T composite with T is the identity. And then the last one, U, will equal U. U acting on U is also the identity. So I'm going to leave you to check those. But now we're going to look at drawing up the Caley table. So we can use these calculations here, draw the table. So we write each element that we've got along the top and then the same down the side. Identity element, we're going to draw that in first. So E, let's just draw that over here a little bit. E, A, B, C, R, S, T, U. And then down the side, similar. Okay, now we've got 8 elements on the top, 8 elements on the side. That's always a good start when doing a Caley table, because it needs to follow the group axioms. The group axioms are that each element inside this table are isolated. So i.e. we can't get, for example, if we had a rotation called V, we couldn't put that in there because it's not part of the table elements on the outside. So let's just separate this up now. So E acting on E, we know is the identity element, so we can straight away put an E in there. We know A acting on C is also the identity, so we can just put that one in there. And its inverse is C acting on A, so that will go in there. B acting on B is the identity element, so that will go there. And then RSTU are all self-inverse, so they will all have their identity following down the line there. Okay, now what we want to do is to try and work out what happens when A acts on A. So if we start from point 1 and we do A and then A again, we're going to end up with a rotation through 180 degrees. So A acting on A will give us B. So that's equivalent as B. Okay, what about A acting on B? So A and then B will end up with a 270 degree rotation, which is the equivalent of C. So that one will go in this position here. We'll write C there. Okay, let's just try and make that a little bit more in a straight line. Okay, now down the outside here, we've got the identity acting on all of these elements. So they are just going to repeat the elements. So we can fill those parts in already. And then A, B, C, R, S, T, U. Okay, well, if A acts on B gives us C, B acting on A will also give us C. So we can write that on there. Now what about C, B? So C acting on B. So if we can write that down and use this formula here. So C composite B. we can use the permutations to do that. So for B, for example, if we use the 1 gives us 3, and then we're using C, which will then give us 2. The 2 gives us 4, and then 4 acting on here gives us 3. So C, composite B, again number 3. 3 gives us 1, and then 1 gives us 4. And then C acting on B again, B first. 4 gives us 2, and 2 gives us 1. So 2, 3, 4, 1 is the same as A. So that's how we can show our C acting on B. And as this group is cyclic, we can flip and B will be the same as C. So that equals also B acting on C. So C acting on B is, what did we say it was? It was A. And then B acting on C is also A. What about C acting on C? So 1 will give us 4, and then the 4 will give us 3. So let's write this down. So 1 goes to 3. So CC, so 2 goes to 1, and then 1 goes to 4. 3 goes to 2, and then the 2 goes to 1. The 4 goes to 3, and the 3 goes to 2. So 3, 4, 1, 2 is the equivalent of our B. So this equals B. So we put the B in there. Okay, so that's the first part of the Caley table, and that takes care of the rotations. Let's have a look now at the reflections acting on each other. So let's have a look now at R acting on S. So 1, 2, 3, 4. So if we take S first, position 1, 1 goes to 1, and then we inflict R on it, well then 1 will then go to 4. 2 on S goes to 4, and then in R, 4 goes to 1. In S, 3 goes to 3, and then in R, 3 goes to 2. And then in this one here, 4, from S, 4 goes to 2, and then in R, 2 goes to 3. So which one does this equal? 4, 1, 2, 3. So going up the line, that equals C, which is a reflection. So we can write that one there as C. Okay, that's R taking care of S. Now let's have a look at R on T. So T, using 1, 1 goes to 2, and then on R, 2 goes to 3. For 2 on T, 2 goes to 1, and then in R, 1 goes to 4. 3 goes to 4, and then 4 goes to 1, 4 goes to 3, and 3 goes to 2. Okay, so 3, 4, 1, 2, that equals B, which is a rotation. Okay, now let's have a look at R and U. R and U. So 1, 2, 3, 4. So U, 1 goes to 3, 3 goes to 2, 2 goes to 2, and then 2 goes to 3, 3 goes to 1, 1 goes to 4, 4 goes to 4, 4 goes to 1. So 2, 3, 4, 1 is the same as A. So that's an example there of how we can build these parts of the Caley table. I'm now going to fill all this in and then I'm going to show you some direct and indirect symmetries. So you'll see here we've got rotations in the top left and the bottom right, and the reflections are in the top right and the bottom left. Now that's down to something called direct and indirect symmetries. So what happens is, for a direct symmetry, you don't need to lift the paper off the table when you're rotating it. But for an indirect, you'll need to lift it to get it to where you want. So i.e. a rotation, you can just leave the paper on the table. For a reflection, to get from 2 to 3, you've got to lift it off and to get it to where you want it to be. Now the rule is a direct symmetry times a direct symmetry will always end up with another direct symmetry. An indirect multiplied by an indirect, this will always yield a direct symmetry. Now vice versa, direct times indirect, these will always yield indirect symmetries. So this table makes this kind of pattern. So if you imagine this one is these ones here, and this one is these ones here, we've got direct, and then indirect and indirect. Okay.